Hello students, we warmly welcome you to our YouTube channel Chemistry Teacher. So here is we are going to present you another lesson regarding organic chemistry that you find in organic chemistry. Students, this time is we are going to present you the topic isomerism. It's here in this lesson, during this lesson, we are going to talk about what is truly this isomerism. As well as we are going to talk about how could we draw the isomeric structures standing for those various formulae of organic substances. Then students, before that, it's one important concept we are going to first consider about. It's the unsaturation number. Actually, this topic, unsaturation number, we are not having within our syllabus, in our A-level syllabus. But students, if you would find it out, how would it be easy that after knowing this concept, knowing this idea, knowing this number, unsaturation number, that we could easily get those isomeric structures. We don't need to work it hard then after. Okay, therefore, before talking about the topic isomerism, let's find it out what this unsaturation number truly is. Students, unsaturation number. So, I'm going to denote it with the letter simple U. Unsaturation. It seems not saturated. Not saturated with what? It is the matter next. It comes. Students, this is all about organic compounds. Therefore, when you talk about organic compounds, you would find carbon. You would find carbon being one element there, playing the major role there. But in the definition of organic compounds, you could find that out. Having only carbon there within a compound is not the only qualification, being organic. So it's either carbon, hydrogen containing substances or they are derivatives we named as organic compounds. Then students, in this matter, when we talk about the unsaturation number, we are finding it out whether it has saturated with hydrogen enough. That means when you have a certain carbon number there, so standing for that carbon number, there would be a maximum number of hydrogen that could be possible. Or let's say derivatives of hydrogen that could be possible for that particular number of carbon. Then students, we are seeking that fact whether we have in its maximum amount what hydrogen. You have seen already that when you have pi bonds there between carbons, it's possible to be carbon-carbon triple bond, carbon-carbon double bond. So you would get pi bonds there. In such situations, it would not be carrying the maximum number of hydrogens it's possible to be there. Let me show you that. So I'll take a substance with 2 carbon. So when it is an alkene, students, it's ethane, this structure. So you are having 2 of carbon with how many hydrogens? It's 1, 2, 3, 4, 5, 6, correct, right? Okay. Then when you have the alkene with a carbon-carbon double bond, it's with 2 carbons still. This is what we call ethene, the very first alkene. So with 2 carbon, you are having 4 hydrogens there. So then when you talk about the alkyne having 2 carbon, for 2 carbon you have 2 ethers only. These are the formulae of alkane, alkene, alkyne. Then when it is about 2 carbon story, so for 2 carbon the maximum number of hydrogen that ever could be is 6. It's not 2, it's 4 is greater than 2, that's why. It's not 4 because 6 is greater than of 4. So you can't exceed this 6. 6 is the maximum, the number of hydrogen that ever could be for 2 carbon containing substance. So therefore, we expect there, when it is 2 carbon, you have there, it has to be 6 hydrogens there within the substance. When you have such number of hydrogens there, or hydrogens derivative, so hydrogen being derived by either halogen, chlorine, bromine, such. So it's possible such as well. So then we call that it is saturated. It is full. It is maximum. The number of hydrogen you have there. But this is not saturated. This is not saturated. We talked about this concept earlier as well. We talked about saturated and unsaturated compounds. But here it's not again the same thing. So beyond that, we are going to find it out. It's when you have 6 hydrogen, then you would find it being saturated. Then students, when it is 4 hydrogen, it lacks 2 hydrogen to be saturated. 2 hydrogen could be given by H2 molecule, one H2 molecule. So we call that the unsaturation number here standing for this substance, this particular substance, as 1. Because if we provide one H2 molecule, it would become saturated. Then we could interpret this. We could define this unsaturation number in the manner as is the number of H2 molecules you need to provide to make it saturate. Okay. Then students, here it is maximum 6, but already you are having 2. It lacks 4 hydrogen. So 4 hydrogens could be given by 2 of H2 molecules. Therefore, the number of H2 molecules it requires there is 2. Therefore, here the unsaturation number is 2. Okay. Now, hope you could have an idea regarding what this unsaturation number truly is. Then students, it's 6 you already have. So it is saturated. Then it needs no hydrogen molecules to be further added to make it saturated. It's already saturated. That's right. So the unsaturated number or unsaturation number is, in one hand, the number of H2 molecules to be provided to bring it saturated. Okay. Then students, in another aspect, I could call this is the number of pi bonds. You don't have any pi bond, therefore unsaturation number is 0. You have one pi bond, then therefore its unsaturation number is 1. So you have 2 pi bonds where you have a triple bond. One would be sigma, linearly overlapped. Then other 2 would be pi bonds. You have 2 pi bonds, therefore the unsaturation number is 2. It's in another hand, I could call it the number of pi bonds you could find within a substance. But it's further, I could show you something like this as well. Students, let's find it out. When you have 6 carbon, the maximum number of hydrogen it ever could be is 40. When it is an alkane with a carbon chain. So this is the maximum number of hydrogen that you would find for 6 of carbons. So I could give it in this form as 1, 2, 3, 4, 5, 6. So with single bonds it's an alkane, so you don't have any pi bond there. So all H's here is the hexane, the respective hydrocarbon. Then it's 40 for 6 carbon, the maximum number of hydrogen you would get. Then you don't find here any pi bond, therefore the unsaturation number is 0. Then student, what about the compound same substance when it is having a cyclic structure, when it is not a linear chain but a closed structure? This is a cyclic structure. This is normal hexane, linear one. This is cyclohexane. We call it cyclohexane. So, cyclohexane is having 6 carbon, 1, 2, 3, 4, 5, 6. When you count, it's 2, 4, 6, 8, 10, 12. It's 12 only, the number of hydrogen. It's not the maximum. It lacks 2 hydrogen. Therefore, it needs one H2 molecule in that aspect to have the maximum number of hydrogen that ever it could be there. Then students, it's though you don't have any pi bond there within a structure, if you have a closed structure, let's say it's a cyclic structure, for one cycle, it will take one H2 molecule, it will take one unsaturation number. Therefore, here the unsaturation number is 1, here the unsaturation number is 0. Simple. Unsaturation number is the number of pi bonds and cyclic structures within a substance molecule that you would find out. Or otherwise, is the number of H2 molecules need to be provided to make it, to bring it saturated level. Okay. Then students, it's when you check for some functional groups, those functional groups would carry some pi bonds with it. Therefore, would have 1 or 2 or such unsaturation numbers taken. As we already have experienced, when it is an alkane having no double triple bonds between carbons, students, it was 0, the unsaturation number taken by the carbon chain. When you get carbon-carbon double bond, you have 1 pi bond there. Then it takes 1, the unsaturation number. When it's a carbon-carbon triple bond, it's you have 2 pi bonds. It's 2 pi bonds there. So it takes the unsaturation number 2. Then students, it's similarly when you have an aldehyde group, it takes the unsaturation number 1. So not only aldehydes but also ketones take unsaturation number 1. 1 pi bond you would find with it. So it's a carboxylic groups, acid group or acid derivatives, you would find having a pi bond there. A carbonyl group would have a pi bond between carbon and oxygen. Therefore, it takes 1 unsaturation number. So then, when it is an alkyl cyanide, RCN, so this cyanide is having between carbon and nitrogen, it's 2 pi bonds. Therefore, it takes unsaturation number 2 there. Then it's those acid derivatives, amides, acid halides, esters, including carboxylic acids themselves, would take unsaturation number 1. As well as aldehydes, ketones, carbonate substances would take unsaturation number 1. It's when it is an alkyl cyanide, that's what I was thinking about. When it is an alkyl cyanide, it would take unsaturation number 2. Then those alcohols, amines and such, alkyl halides, they won't take any unsaturation number. Ethers, so it's no pi bonds you find there within those structures. Therefore, as a functional group, they do not take normally unsaturation number. This is going to play a very, very important role there in finding out of suitable isomeric structures that we are going to talk there about. Okay, that's what unsaturation number is. Then when we check for a cyclic structure, we have already experienced cyclohexane that having 6 carbon is a hexagonal cyclic structure. It took unsaturation number 1 there. Then students, let me show you what benzene is. C6H6 is the formula. So it also is a hexagonal structure, but it's to have alternative double bonds there within the structure. Normally we draw it in that manner, that form. So then when we talk about benzene, it takes, it's 1 pi bond, another. It is 3 pi bonds you have, and it's a cyclic structure as well. Then 3 pi bonds, they are for 3 the unsaturation number. Then for the cyclic structure, we could give another unsaturation number. It's altogether 4. Benzene, aromatic structures, they take unsaturation number 4 there. Okay, then it is going to be very easy. Identification of which kind of structure I could draw standing for this molecular formula when you are provided with a molecular formula. Okay, students, it's seeing the molecular formula, we could predict what's the unsaturation number standing for that compound as well. So it's with your early sense as for C2H6, you might say it is ethane, so therefore it would take unsaturation number 0 because it's an alkane. It's your experience now. It's your recognition as it is an alkane. But you shouldn't by heart or memorize all those stuff. So it's okay at the very beginning if you feel it like this is an alkane, this could be an alkene, this could be an alkyne, and such stuff. Then therefore this takes unsaturation number 0, 1, 2 respectively. So it's okay, it's good, but you don't need to waste your kind of memory regarding that thing. That thing means by hearting those molecular formulae as whether it's an alkane, alkene, alkyne, those facts. So students, we could easily get the unsaturation number there observing the molecular formula given using this formula equation. So you could simply multiply the number of carbon by 2 and you add 2 on that. Then you subtract the number of hydrogens you find there. Then you deduct number of halogen atoms within the molecular formula that you find. It's okay if you do not have any, but if you have, please deduct. Please subtract those halogen atoms, number of halogen atoms there. If you find nitrogen atoms, then you add. So it doesn't matter other atoms like oxygen, sulfur, any such. So we don't take those here to this equation. So you add them up, or you add these, multiply this by 2 and add 2 and subtract number of hydrogen and subtract number of halogens and add number of nitrogens there, and finally you divide it by 2. So then you could easily obtain the unsaturation number without trying to draw the molecular formula. It is the molecular formula without trying drawing of structural formula. We find it out what's the difference between molecular and structural formulae. We'll find them out. Okay, students. Then when we apply it here, it's 2 carbon you have. 2 into 2. It's 2 into 2. It's plus 2 minus number of hydrogens is 6. You don't have other atoms divided by 2. Is the U standing for this? It's 2 into 2 is 4 plus 2 is 6 minus 6 is 0 divided by 2 is 0. You could easily get the unsaturation number standing for that is 0. See how easy is that? Then students, I'm going to show you another few sites and then we'll switch to our main topic. So students, when you have C4H8, let's say, it is 2 into 4 is 8. 8 plus 2 is 10. Minus 8 is 2. Divided by 2 is 1. Its unsaturation number is 1. It could be either a carbon-carbon double bond, means a pi bond within the structure you are having, or otherwise it's possible you to have a cyclic structure. See how easily we could predict which kind of structure it could be. That's the advantage of knowing this concept, unsaturation number. Then students, it's when you find something like C10, H18 and oxygen, then students, it's 2 into 10 is 20. Then 20 plus 2 is 22. Minus 18 is what? 4. Then divided by 2 is what? 2. It's having its unsaturation number 2. So it's possible you to have carbon-carbon triple bond within this structure. It takes 2. Or carbon-carbon, 2 of carbon-carbon double bond. Once. So it's one carbon-carbon double bond and one carbonyl group, because you have one oxygen there. So it's one cyclic structure and one carbon-carbon double bond, or one cyclic structure and one carbonyl group. So you could imagine various possible combinations, imagining the number of pi bonds, what it could be, or number of cyclic structure matching with the number of pi bonds. That's the advantage of knowing the concept unsaturation number. Then students, when we talk about that formula, that pressures formula, what is the C6H6? We drew a little while ago, we drew the structures for that. Namely, it's the benzene. Could you remember? We showed that it's alternating double bonds, 3 of them you have, and cyclic structure, therefore it has to be 4, the unsaturation number. Let's check whether it's the same giving us using that equation. In students, you have 6 carbon into 2 is 12, plus 2 is 14, then minus 6 is what? 8, divided by 2 is 4. It's you are having unsaturation number being 4. It's when you find within for given molecular formula, when you find its unsaturation number being 4, it most possibly could be a benzene ring, therefore an aromatic substance. Okay, that's the advantage of knowing unsaturation number. Then students, let's start doing our main topic. Is what? Isomerism. Students, what isomerism truly is? Isomerism. Before giving you that idea, I need to introduce you few terms that you need to know about. You consider this C2H6. You would say it's an alkane, it is ethane and such stuff. So I could represent the same thing in this form. CC, it's then it also ethane. What's the difference between them? Then I could represent the same thing in this form as well. So it's three-dimensional, imagining it's three-dimensional way of spreading those atoms. I could just give you the idea how the geometry of those atoms, their bond length, bond angles and those, I would show those in such a diagram. So then further I could see that it is between C and hydrogen, carbon and hydrogen, the ratio you are having is 1:3, not 2. It is CH3 therefore, the simplest ratio. So atomic ratio, that into 2 is giving you this. Okay, I could represent the same thing in these all different ways. What are the names standing for those different types, modes? Students, when we have the exact number of atoms representing the substance, it's we call the molecular formula. Molecular formula there. Formula. Then, when you have this kind of structure, as what we call Lewis structure, it's the Lewis structure, or we could call it the structural formula. Structural formula. Then what about this? It's the geometry. It's the geometry of that substance. Then it's giving us the exact idea of how the structure is. What are the bond lengths and bond angles and such stuff, orientations. Then we call that the structure. structure. So you forget about this part, the simplest atomic ratio that you get within the substance. So that is the empirical formula. Empirical formula. Okay, those are different representations standing for the same species. Then what's the isomerism is? Students, isomerism is having of different structures for the same molecular formula. Having of different structures for the same molecular formula. What's that? Having of different structures for the same molecular formula. It's quite like having the same name. There could be few or many people out there that you find. You could find many different examples that bearing the same name. It's possible to find out different people out there. Okay, similarly, when it's the same molecular formula standing for different substances, that's what we call the isomerism. It's the having of different substances for the same molecular formula. For sometimes it's possible. It's representing different structures. You could have one molecular formula there. So it's just because you get the exact number of atoms only. The details what you get, exact number of atoms only by a molecular formula, from a molecular formula. But when it comes to a compound would be having its atoms distributed in a certain way in the space. But it's possible some different distributions of those atoms you find there having different compounds representing different compounds, but when you count for the number of atoms, that element's number, that elemental atom's number, then those would be the same. That incident, that phenomenon is identified as the isomerism. Students, simply isomerism is having a different, it's having a different compounds. A compound is having one structure only, one particular structure only. Therefore, it's we could call having of different structures. Having of different structures for the same molecular formula. Is the same molecular formula. So, it's you could find various different compounds therefore standing for the same molecular formula. It's when there is a compound doesn't care what's the molecular formula, what's the number of atoms based on that, what's the name or molecular formula they are giving on me. So, molecules, they exist in nature. So, then it's us worrying about. Is that compound having these atoms? Is that compound also having the same number of atoms, same atoms? Then it's the same molecular formula you get for this compound as well as for that compound. It's our concern. We are worrying at that. So it's then possible to be troublesome. It's possible to kind of create some problems as well. It's possible to miscommunicate for some times. When you give a molecular formula thinking on a substance, but if the other one perceive something else, it's another substance standing for the same molecular formula, there is a communicational error. So then we need to be aware, well aware of all the probabilities, all the possibilities that this molecular formula we are having could be. Then only we could overcome such problematic situations. That's the point. That's the point of learning this thing. We are going to find it out, for sometimes it's for the same molecular formula possible to have different compounds representing same molecular formula. You could have different compounds there. So we need to learn how they would be different. They would be different from each other. Then only we could develop this awareness of all those organic substances. Then only we could communicate healthily with others regarding the substance we need. That's the purpose that why we learn this. What? Isomerism. Okay, this is the isomerism. This is the definition, having of different substances representing the same molecular formula. So far we looked at another term. We have looked at the structural formula. It's the Lewis structure. So it's still not giving those informations how are the bond lengths and bond angles they arrange there in the space. But they state which atom has attached to which atom and how many bonds between them you get. What is that a single, double, triple bonds? Such informations you could find out there looking at the Lewis structure. Let's call it a structural formula. Then students, for sometimes you would find same molecular formula carrying different structural formula, therefore they have different substances there. If you find your isomeric structures, such structures, those which have the same molecular formula but different compounds, their structures, such structures are called isomers. Isomers. Then when you have isomers, you could find those isomers being having it's through different structural formula for sometimes. You could clearly draw two different or few different Lewis structures, structural formulae. So therefore they are different even from their structural formulae. Therefore, for the same molecular formula, if you get isomers having different structural formulae, we call that a subcategory of isomerism is the structural isomerism. So we identify the same term in another word as a constitutional isomerism. They have different structural formula, therefore it's obvious they have different compounds, different structures. So if I define that, it is having of different structures through having of different structural formulae for the same molecular formula. It has to be always for the same molecular formula. For the same molecular formula. That's the constitutional, or we could call structural isomerism. Again, it is the having of different structures through having of different structural formulae for the same molecular formula is called constitutional isomerism or structural isomerism. Students, then it's the first subcategory. Means there are two types of isomers or isomerism that you categorize. So this is one category. You have another category. So at that time, they won't have different structural formulae, then they would have the structural formula also being the same. Not only the molecular formula, but also their structural formula also is the same. Then students, there would be still different compounds being arranged differently in three-dimensional space. In 3D space, their arrangement would follow different orders. It's what we call, let's say, three-dimensional isomerism or stereo isomerism. Stereo isomerism. So it is the second type, three-dimensional or stereo isomerism. Second type. So if I define that, having of, always it is having of different structures. Having of different structures, but for this times it's not having different structural formulae. It's same structural formulae, although the structural formula is the same, but having it's through having different, we could call it arrangement in three-dimensional space. So we could call it spatial arrangement. It's different spatial arrangement. For the same molecular formula, it has to be always for the same molecular formula. So students, it's very easy. For this time, it's you have this for the same molecular formula, you have different compounds. So they have the same structural formula as well, but they are spatial arrangement. In the three-dimensional space, their arrangement of atoms would follow two or few different orders. That's what we call stereo isomerism or three-dimensional isomerism. Okay, then we learned about the first means it's two categories that isomerism you would categorize into. Then what? Then what would we have? If you are going to further discuss about this structural isomerism, as it's having three types, three categories. Students, one is called chain isomerism. It's the chain isomerism. I will explain that. Then the other one is called position isomerism. Position isomerism. The other type is called functional group isomerism. So there are such three types. One is the chain isomerism. What they are having is they have different structural formula. They are for different structures through having different lengths, carbon numbers in the main carbon chain or carbon chain number. The carbon number in the main carbon chain or long carbon chain would be different. You could reduce carbons and attach them again to the chain as branches, methylated propyl groups. In such a way, you could reduce the carbon chain. So it's actually we are not reducing the carbon chain. It's you could have substances with such arrangements of their atoms. In such a situation, when you get more than one structure for the same molecular formula, having different structural formulas still, but they are different structural formula through having different lengths of carbon chain. So we call it the chain isomerism. Then what's the position isomerism? So students, it's on the carbon chain of a compound, organic compound. If you find either a functional group or alkyl group, it could be a double triple bond or any other functional group located there on the chain, carbon chain. That position of that functional group or alkyl group could get changed for another compound. It's another compound. But they are having the same molecular formula. Then having different positions in the chain of those functional groups, we are going to find out some examples for this. But those functional groups or alkyl groups, their position being different, they have different substances. For the same molecular formula, they have different substances through having of different structural formula. That's what we identify as the position isomerism. The position get changed. Then it's easily you could find out what's the functional group isomerism. If you got that earlier too, it's when it's saying chain isomerism, it's the carbon chain length get varied. When it says position isomerism, the position of groups attached get varied. When it says functional group isomerism, the functional group's type could be varied. In such situations, you would get different structural formula, therefore different structures, but for the same molecular formula mainly. So it's what we call functional group isomerism. Okay, then students, this stereoisomerism or three-dimensional isomerism also has got some categories. Actually, there are two categories. So the first type is called geometrical isomerism. They have the same molecular formula as well as same structural formula, but when you have, they are geometrically different. When you actually, we are going to talk about these in more details. It happens when you have a carbon-carbon double group, and the arrangement of other groups, when they get kind of different, when they are different one to another, giving different spatial arrangement, we identify it as geometrical isomerism. Or we could call it is geometrical isomerism, as well as it's diastereomers what you get there. So it's let's call it cis-trans isomerism or diastereomerism or such we could call it. We'll find them also. Then students, it's next one is the optical isomerism. The next type out of these two in the stereoisomerism. One is geometrical, other one is optical. When you have one carbon having four bonds attached to four different groups, they have to be different, four different groups. Then they would arrange tetrahedrally in the space. When you get that tetrahedrally arranged four different groups around one carbon, when they get arranged in two different ways in the space, is what we identify. Those are two compounds that is what we identify as the optical isomerism. There is a reason for naming it as optical. Optical stands for light. We are calling it optical because it's the method we could distinguish them. When we pass monochromatic plane polarized light, we are going to learn about this soon. So then only you could distinguish one apart from other. And that's why we call it, that's the reason, we call it optical isomerism. So students, if you have geometrical isomerism as well as optical isomerism. So then those are the stuff what we have in this lesson, isomerism. Again, it's the incident or it's the having of different compounds, different structures for the same molecular formula. We call isomerism. Then students, you could find these different structures being given, giving different structural formulae. Already you know, structural formula means the Lewis structure. Those substances, different substances of same molecular formula would have different compounds. Their structural formula also would be different. Okay, then we call it structural isomerism or constitutional isomerism. Those structures would be different, having different lengths of the carbon chain, then the position of those functional groups or main functional group or alkyl groups. They are on the carbon chain, varying the position. Then it's the type of the functional group being varied, being different. You could have different compounds through different structural formula. That's what we call structural isomerism. Then, although you have the same molecular formula and same structural formula, it could still pack or arrange in the space differently. One way is when you have a carbon-carbon double bond carrying two different groups on each carbon, their arrangement could follow two different ways. Is what we call geometrical isomerism. We are going to find that out. So it's next is the optical isomerism. Students, it's when you have one carbon carrying four different groups tetrahedrally arranged. So then it's those four different groups around the carbon could pack in the space differently. In two different ways it's possible. Then it's what we call the optical isomerism. Optical isomerism. So it's we call it enantiomerism as well. The isomers are named as enantiomers. Here the geometric isomers are named as diastereomers. Those are the stuff we have got towards you in this lesson regarding isomerism. So it's we looked at point that what is truly this isomerism stands for. Then students, our next effort is finding you in our next video talking about each type, giving examples. What is the chain isomerism, position isomerism, functional group isomerism, as well as geometric, optical, such isomerism. Okay, that's our plan. So, we are going to meet you in our next video talking about these three types of isomers. It's the what? Structural isomerism. Then after we are going to meet you with these two types of isomers. It's the stereoisomerism. Students, these are very easy few things, few points that you need to know. So here we discussed or we considered about the what? It's the unsaturation number first, then after the concept isomerism. Okay students, that's all we have got here in this lesson, this video towards you. So we are going to round up here, willing to meet you in our next video. Okay students, goodbye.